in the world. Morning crew, and welcome to the Andy Mechanic YouTube channel, and Tool Girl Sam is back. It's been a while, hasn't it?
Yeah,
I've
been busy.
Busy. We've all been really busy. I've been away pretty much the whole of the last 4 weeks by about 5 days. So my apologies, people, for not posting any videos for the last 4 weeks. Really sorry, and I'll try not to let it happen again, but just impossible. But there's some great news, because Tool Girl Sam has a new shirt. Look at that. Bloody cool. And of course, I get one as well. Yeah, but yeah, I'm almost irrelevant when Sam's on the camera. She steals all my thunder. Is that you?
It's the new shirt, that's all it is.
Is that what it is? Give us a twirl, girl. Let's have a look.
Oh, there's something on the back.
There is. Look at that. Andy Mechanic everywhere. So I reckon it's going to work out to be a pretty good camera kind of shirt, because it's got that Andy Mechanic logo. Many different dimensions. Yeah, and what
Who am I watching? Andy Mechanic.
Yeah, that's the idea. Because people steal my pictures. They steal them off the video and they use bits of video.
And people steal my pictures and use them on dating websites, so...
Is that right?
I'm not the only one.
Jeez, that's no
to
good.
a lot of people.
If I find somebody, I'll have them shot for you. How's that?
Please.
My favourite logo on this shirt, and it was a last minute thing, is that. I really like that. Like, it gives it
I noticed that straight away.
A bit more credibility, you know. And it really is the second best place in the world. Is that? That's where I grew up. Obviously, New Zealand has to be the best, because I'm still here and I didn't go home. Right, enough banter. We need to do something. So this video is all about why we use oscilloscopes and just how bloody easy they are to use, because I'm going to show Sam how to use an oscilloscope, and then she's going to show you how to use an oscilloscope. It's a doddle. It's so bloody easy. Now, multimeters are great. You know, we've all got multimeters in our workshop, and if you go to any kind of wiring and stuff, you have to have one of these. But when you're trying to measure a voltage that's changing, say a signal on like a fuel injection system from, let's say, I don't know, a TPS sensor, or crank angle sensor, you know, especially a crank angle sensor, you've got a signal that's changing voltage very quickly. Even at idle, that crankshaft's spinning around pretty quick, and it's a square wave signal or whatever it is coming from that sensor. It's you know, changing its state very quickly, you know, maybe hundreds and hundreds of times a second, and you just can't measure that very well with a multimeter. Sure, if you've got duty cycle on there, then you can get some idea of a percentage and it gives you a bit of an indication, but it's not conclusive. And because in the last 20 odd years cars have become so much more complicated with your fuel injection systems and all these sensors and actuators and signals flying around under the bonnet telling things to do stuff from the ECU and telling the ECU things, diagnostics has become extremely difficult without the right tools. And very fortunately, and hence why they're on the shirt, I have that much respect for these guys, Picoscope sent me an automotive style oscilloscope. Now, for those of you that watched my videos previously, I do have another scope, oh, it's hidden away somewhere, which is the 2000 series, cheap as chips, 220 odd New Zealand dollars, and I've done lots of stuff using that. And actually most of the MR2 diagnostics that I did a few weeks ago was using that 2000 series scope, cheap as chips, and really not really much more expensive than a decent multimeter. And then on the last video, this had arrived. I thought, right, 4-channel scope, perfect. Let's link up the fuel injector pulse. Let's link up the IGT and the IGF on 3 of the 4 channels on here. And we proved that the new ECU that we fitted, everything was working correctly, and the waveform out of the IGF was perfect. See, memory's getting old. Okay, right, so we're going to set up a really simple circuit first of all, of just a bulb and a switch, and then we'll do a comparison test with a multimeter and the oscilloscope. Now, bear with me, I have got a bit of cold at the moment, so if I start coughing and lose my voice, just ignore me. It's all right. Just look at Sam instead. Right, here we go. Okay, Sam, real simple circuit. We've got our power supply. And somewhere is, God, where did I put everything? Hang on. Right, so there we go. Bulb. And a switch. And this might be enough leads, or maybe we need some more leads, we'll see. Okay. So if you, do you want to hook that on the positive for us? On there, look. I like
So
to use,
that's the red one.
it is, yeah. Stick it on the red one. And stick that one on the black one for me. There you go. That's going to give us power, you know, just like a normal battery. You've got positive and negative. All right. And we'll do it negatively switched. This is our switch here, look, so we'll stick that on there. A bit bigger, these clamps. I'll stick that one on there. That works. And then, very simply, that goes on there. And with a bulb, it doesn't matter about the polarity, it's irrelevant. That goes on there. And now, if we turn on the power, and then we turn on the switch, hey presto. All right, real simple.
Light.
Real simple, we've got light. So I'm going to pass the switch to you, and the reason why will come apparent shortly. Okay, so, multimeter. Let's get this rigged up first. And just behind you, on that hook, there's some more of these leads. Could you pass me a few more over?
Colour doesn't matter.
Nah, colour's irrelevant. My wiring's bad enough as it is. Okay. So first of all, we're going to plumb in the multimeter. And we'll stick that on there, look. That's negative switched onto there. And then have a ground, cheers Sam, onto there. And then, well, when we set the meter up correctly, we should be laughing. Right, there we go, look, so we're on the, should be on about 12 volts. Okay Sam, so I'm going to hold the bulb this time, and what I'd like you to do, I know you can't see the multimeter, but I want you to turn the switch on and off for me. Alright?
Is this it?
Yeah, so you just flick it one way and the bulb will come on. Go on, you can do it. It's a bit stiff. Hang on. I'll show you. Hang on. So it's like that. It's a switch.
Twist it.
There you go. So
Okay.
hold it with the other hand. There you go. Alright. Cool.
Ha.
Now if I just twizzle this around for a second, if you flick that switch as fast as you can.
12, 6, 12, 5, 12.
Yeah, the meter's
5, 7, 3.
it sort of keeps up, doesn't it? So if you slow down, if you just switch it, say, oh golly, hertz of 1, so 1 per second.
Staying alive.
That's the one.
Staying alive.
So the multimeter, it's
Oh,
you
shit.
destroyed it. It's all right. I think it goes on that one.
Oh,
There we go. Right. So the meter sort of keeps up. When the bulb's on, we've got 12 volts. When the bulb's off, we've got 0 volts or thereabouts. But if you then flick that switch quite quickly, the meter very quickly gets out of sync and it can't
Gets
really see what
confused.
it gets confusing, and it almost becomes gobbledygook.
Oh
you know?
heck, they keep falling off.
Middle one this time. Cool. Okay, so what we'll do is we'll plumb up the oscilloscope as well, and then we'll do a comparison between the two, and then we'll find something that can switch a switch a lot faster than you can.
Okay.
Hopefully, we'll have something like that.
Sounds
Right.
fun.
Blue. Okay. So now we need to pick up exactly the same as where the multimeter is. So that's that one there. We can stick it onto there. On that one. And then the positive. Are you yawning, girl?
Yep.
You're gonna make me yawn, aren't you, as well? Right, where's the other bit? Oh yeah, look. So stick that one on there. Cool. Okay. Okay, now, Sam, you've got to learn this, haven't you? So, if you come and stand here,
Learn.
right, so when we fire up the laptop, fire up the scope, we've got all this sort of gibberish going on. Now, if we turn that off, it shouldn't really make too much difference, but we've still got a lot of white noise. So, what we need to do is set up the scope so that it's going to be able to record the right voltage and the right time frame. Now, at the moment, the change in state is very, very slow, isn't it? You're turning the switch on and back off again, and it's quite a slow switching process. Very different to what you'd find, you know, with a, let's say, a crank angle sensor that's going to fire out maybe, you know, 1,000 pulses a second, depending on the engine RPM. So on here, look, Sam, we're on channel 1, which is the blue channel, channel A. And can you see the A up here, look?
Yep.
On the screen. So what we need to do is go onto here and choose a voltage first of all. Now, the power supply is 12 volts it's set to, so we'll choose 20 volts and then we're going to be within range. And then we also need to choose a time frame, and we've got 5 milliseconds division, which probably is too quick for what we're doing. So what we'll do is we'll go on to seconds, and we'll do, let's say, so each box on the graph would be a second. So we'll choose that one. There we go, look. Okay. And now, I'll turn on the power, and we'll just get hold of the old switcheroo. Okay, so if you come and stand where I am, and you can operate that switch, and we should see, there we go, look, on the screen. So now you can do it so the same kind of speed you were doing before. So you can see that whenever it's 12 volts, we've got the line high, and whenever it's 0, the line is low, because this is your voltage scale down here, like you see, 0, 12. So try and do it as fast as you can to confuse the scope. Look at that. Whereas the multimeter is all over the place, isn't it? Really, we're not getting a consistent reading at all out of the multimeter, because it should either be 12 volts or thereabouts, or 0. But we're seeing 6 volts, 7 volts, all sorts of stuff. Everything. Okay. So what we can do now with the scope, just have one more go, and then I'll pause it. Cool, that'll do. So we can pause that. And now, if we want to, we can actually zoom in on stuff by going on to there, I think it is. There we are. With it being touchscreen, it's pretty cool. We can actually use a touchscreen as well. So you're starting to see a lot more detail. This is while the switch is turned on. And when you turn the switch off, you can see we're getting a bit of it's changed. It's not a nice clean square wave. We're getting this sort of weird, as the contacts are parting, there's probably a little spark going on there inside the switch. So we get to see a lot more information
That's crazy.
on a scope, than we would ever see with a multimeter. Yeah. Okay. So I think the next thing we should do is, rather than you have to stand there turning the switch on and off all the time, which gets a bit laborious, what we'll do is we'll wire up a flasher relay instead, and then this can do all the click on, off, on, off. All right? Cool. Plan of attack. We can get rid of the switch now, and that was a negatively negatively switched switch, so that's both negatives and all that. So with our flasher relay, we've got a B. Okay, we've got an E. So B is battery of 12 volts. So what we'd better do is grab that one. Did I turn it off? Nope, turn it off. I'll make smoke otherwise. You know what I'm like. So we'll stick that on there. That's our power in. And then we need a ground. Well, there's a ground, so we'll stick that on there. And then L is for the light. So let's steal that one. Okay, so that's power in for the light. So Sam, if you want to stick that on the L pin for us.
Like this way?
Yep, that'll be fine. Yeah, as long as it's connected, that's all that matters. Now also, the bulb, that's our power coming out of that flasher relay to the bulb. The bulb also needs a ground as well, otherwise it won't work. So stick that on there. And then, if you want to see if you can get that on the back there, look, with that other ground.
With the other black one?
Yep, somewhere on there.
I clip it just on the black one.
Yeah, you can do. Yeah, onto the other clip, that'll work. Okay?
Yeah.
Excellent. Right, so we'll just test it. So we'll turn the voltage right down. You'll turn the power on. And then if you want to turn that dial, can you see the volt gauge here? Look, see if you can turn it to sort of just over 10, maybe 11 volts, 12
That
volts.
one on the left?
Yeah, volts is the left hand one, that's it.
So 10.
Yeah,
Am I
keep
doing
going.
it slowly?
No, you can go straight there if you want. There you go. Keep going. See if you can get it to 12 volts or thereabouts. That's what it's supposed to run at. Perfect. So now, all of a sudden, you're redundant. We don't need to switch the switch anymore, so you can bugger off.
Okay, sweet. I'm done.
Done. Don't like that. I like being here. I like to learn. Right. So what we need to do now is rig up the multimeter and the scope. So we'll do them one at a time. So we've got our multimeter here. Look, we need some more wires. As if always need more wires. Make sure they don't touch. Okay, so the green one is our positive. So we'll stick that on there. And we can use that as our negative. That goes back to negative on there. So we need one more lead. Oh, we're on yellows now. Jeez. I'm amazed why I don't get so confused, really. All right, so there we go. Look, so there's your multimeter, and that's now it's sort of
Skipping.
yeah. It's already out of its depth, isn't it? It almost can't really cope. See if the people can watch that. In fact, bring it a bit nearer. See if you can see that. Can you see that? Yeah, you can sort of see that. Perfect. Definitely see that now.
This thing in here is going. Eep, eep, eep.
Oh, the fan. Yeah, I don't know. I think it's got like a personality as the fan. It doesn't really know what it's doing.
It's just jiggling its head.
I don't know why. No idea. I'm sure one of the viewers can tell us why the fan does that. Okay. So next job is we need to plumb up the oscilloscope. Now this is pretty easy. So this is the positive, so that can go straight onto that probe there because that's all positive. So we'll stick that on there. And that's negative. Cool. So we should be good to go. So Sam, if you stand here, and then all you need to do to restart the rig is see the little play button there. Look. You see it down here. Look. You see that little play button. So if you click on the mouse, just click down. That should start it recording again, and we should see. Oh, get rid of the zoom. We've got a zoom on at the moment. Get rid of that. There we go. So now we're getting a really rhythmic signal.
Well, it looks even.
Yeah, it is even. It's exactly what it is. You know, and it's you've got the peaks again of the 12 volts. That's when the bulb's on, and you've got the valley, which is 0 volts, and that's when the bulb's turned off. And this is an electronic flasher relay now, controlling that pulse, and we're seeing a square wave. So, and again, you can see on the multimeter, it really is struggling to give us an accurate reading. We're right on the edge of it being of any use. Yeah. You see it on an oscilloscope and you say, wow. And we can play around. So we can move the multimeter out of the way now. Actually, I think we can pretty much say that's redundant. But we will bring it in later on to show how bad it can get. But if you go up to, let's say up to the time one here, look, the says 1 second division. If you click the down bit on there, and let's say we choose a longer time frame. Choose maybe 5 seconds per box, and see how that changes the graph. Yeah, so now it's bunched the whole thing up, and we can see a much longer period of time across the screen. So basically, the faster these pulses would be, the lower we'd have to set that time base, that time division. Otherwise, we may not see it. So let's say if you go back on there again, and let's say we use a really short time frame. Let's use 1 millisecond up here, look. Click on there. And now we're not, all we're seeing is either a trough or a peak. We're not seeing the full waveform on the screen because the screen's refreshing too quickly. Yeah. That time across the screen is too short. So if you go back onto, let's say onto 5 seconds again then. There we go. We get our little wave back. Pretty cool. And at any time, once you've captured your waveform, you can press the stop button down there, and then you can zoom in and you can analyse that waveform and look for, bits that are not correct. Yeah. Anomalies.
Yeah, well, it was all perfect, and then now it's starting to go like a little jagged.
And I wonder if we crank up the voltage a bit, that might.
Tired.
So, there you are, look, you crank up the voltage. So now we've stepped up the top voltage. We're running about 16 volts, which is going to probably
Super bright.
Yeah, really bright for the bulb, but it's probably going to upset the flasher relay bit, so we can bring that down. And we could also do a little experiment and see how low a voltage it'll keep running at. So I'm just going to keep turning this. In fact, you can do that. So very slowly turn it anti-clockwise, and we'll see. I mean, you'll notice the bulb stops flashing. We'll see what the lowest point is that flasher relay will actually actuate. Oh, look at that. It's pretty cool. So it's still running around about, well, the voltmeter's saying around about, oh, it's stopped now. So go back up a little bit. There we go. Let's try and get it on the minimum point. Wow. See, it was running right. It was running really low down here. Look, it was still actually triggering, even though the bulb wasn't lit.
Yeah, can hear it when it does.
That is fantastic. So I can pause that now. Press the stop button, and then if we want, we could zoom in just on those bits there. Look, and you can see even there. And I wonder what if you think, oh, I wonder what voltage that peaks at. Then we can actually, if we go back to here, we can actually grab the little measurer and we could line it up with the peak. And that's running at 0.2 of a volt. Wow. What an awesome flasher relay. Okay, so we've done the switchy thing. We've done using a flasher relay, but we've not done something yet which is going to highlight the limitations properly of the multimeter. So I came up with a little plan. If you can stand back around there again, Sam. This is
another one of those.
Yeah, this is a 5-pin relay. So that's a flasher relay. This is what we call a changeover relay. So basically, it has. Oh, we should do a diagram. Let's do a diagram. We haven't done a diagram for a while. Right. Let's turn all this stuff off for a minute. Okay, Sam. This was my ingenious plan. So we've got a 5-pin relay, and my eyesight's shit these days. So let's just bear with me. So we've got 30. Because all the terminals have got numbers. All right, we've got up here we've got 87, and then we've got 87, A for apple, and then on this side we've got 85, and on this side we've got 86. Okay, so 85 and 86, that's our trigger circuit. All right, and so that's basically what controls the relay. So we run 12 volts between 86 and 85 like we did the bulb, and that will energize a little winding inside, which will then flick a switch. And the switch part is this bit here. This is the actual switch here. Okay. So when we don't have power to this, then that terminal and 87A, so 30 and 87A are connected inside. When we put power to these two, 85, 86, that flicks the switch internally, and now 30 and 87 are connected. So it disconnects that one. So what I thought we'd do is turn this into a super fast switch that's going to work all on its own. And the way to do that is we're going to put 12 volts onto 86. Okay, but rather than put 85 to ground, we're going to wire 85 onto 87A. All right, and then 30 we're going to put to ground like that. Okay, so what will happen is when the switch is turned off, we get current flow from 86. Sorry. Turn the switch on, so we energize 86, 85. We get current flow flowing through the winding, and we can actually do that here. Look, we can put a winding down to 85. There we are, look. Okay, so we turn on the power supply, we get current flowing through the winding, 85, 87, down to ground. But as soon as we energize that winding, the switch inside is going to flag. So it's going to break the circuit between 87A and 30 because it's going to connect 87 and 30. Instead, it's going to go click across inside. But as soon as it goes click across inside, it breaks the circuit to the winding, so we get no current flow. So then it turns off again and it goes click. And it does this really, really fast. And it's not something, the relay wasn't designed to do this, but it does give us something which is going to switch very, very quickly, and it's going to confuse the hell out of the multimeter, and it's going to make the oscilloscope look fantastic.
Yeah.
Okay. And I haven't seen this on the scope yet, so it should be pretty interesting to see what we get. Okay, right, you can get rid of that. It's all in my head. All right, so plan of attack, we need to build a circuit. So, what do we say? We said we wanted power in on 85, so we'll honk that on there like that, look. That should work. Maybe like that, be better. Okay, and then we were going to go from 86 onto 87A. So, there's 86. Alright, pop that on there. And then 87A is that one. So we'll just put the sheet all around it. There we go. Alright, and then 87 goes nowhere. That's just, we could always run something off that if we wanted to, but it doesn't matter. And 30 now has to be a ground. So that is our ground. There we go. Alright, so the relay now is wired up. So if I turn that on, it's going to go, it should go, alright, you ready?
Yeah.
Okay. It's like, no, leave me alone, stop it, it's not fun. Okay, can't cope with that. Right, so we'll have negative on there. And the positive, now, I'll get this right now because I probably choose the wrong one. Small lead. Okay, positive on there. Okay. Okay, that should be the one. Okay, always off the cuff. Right, so power on. Oh, power on, voltage up. There we go. So what's the multimeter doing?
It's actually going up instead of being like.
Alright, so the voltmeter is giving us about 9.5 volts. Pretty constant, but we know that there's something not quite right going on down there. Alright. So now we can rig up the scope. So I'll just turn that off again. It probably isn't doing the relay any good at all at the moment.
No, it sounds like it's in pain.
It does. It's like, killing me. Okay, so we can get rid of that spare wire. Alright. Okay, stick that on there so we get exactly the same pickup for the scope. I'll stick that on there, look. Alright, Sam. So what you can do now is you can press the play button again. We'll see what we get. Alright, so power on.
Are we too zoomed in?
Yeah, that's what it is. So we can just zoom.
So weird.
And now we've got a warning sign on there. You see it says channel over
range.
range. So we need to change the voltage. So if you go up to voltage there, let's see it says 20 volts.
Where's my mouse? There it is. It's so small.
And then whack it up to maybe 100 volts. And I'll explain to you why. Oh, we're still getting over range. Okay, so pop it back onto maybe 200 volts. Is that going to help? Damn, no. Okay. So what we need to do now is use one of these. And what this does is it reduces it by 1 to 10. So if we've got 200 volts, and this is an induced AC voltage that we're seeing here, because of what's going on inside the relay, we've got a coil that's energizing and collapsing all the time really quick, and that self-induces a current, and that's why we've gone from being 12 volts way up high. It's going to die. Okay, so we'll plug this in, and that should then give us a very different reading, and one that we can actually comprehend on the scope. You see, just drop right down. So that's divided the voltage, the induced voltage, by 10. So now it's within our scale range. All right, Sam, if you come back around here again, you can set that up. So we had, I think 50 volts we said should be enough, didn't we? Because we put that attenuator in there now.
The volts is on auto.
Yes, you want 50, I think, on that one. There you go. And as regards the time frame, you're on 5 millisecond divisions. So what were we on before? I think we were on about, when we were doing the flasher relay, what was the, I think it was about 5 seconds, wasn't it?
Mm-hmm.
So put it back on 5 for now, and that'll give us an idea of, there we go. Okay, so I can turn it on again. And we just get gobbledygook on there.
Mm-hmm.
We're getting a pretty constant 8.79 volts. There, look. 9.5, 9.6, 9.5. But we know it's switching. And the multimeter is telling us we're getting a constant voltage. And the reason for that is it can't see that switching fast enough because of the refresh rate on the tool. So what we can see on the screen. All right, so we've got one last thing to have a look at. We just passed through that distributor that's on the bench there. Look, yeah. So basically, cheers. So basically, this is what you find on a car. All right, on an engine normally. Most modern engines will have these. And we've got a pickup. Now we can tell from this it was a 4-cylinder engine that this came from because it's got 4 little peaks on that rotor. And when this is actually connected to the camshaft of the engine, so it spins at camshaft speed. So as the cam spins, you'll find that this is spinning on the engine as well. And as each of those little rotors goes past that sort of metal plate, it induces a voltage. There's a coil of wire inside that plastic casting. And every time it spins past, it induces a voltage into that sensor. That's a pickup coil.
Interesting.
Yeah, so we can put this in the vise, we can spin that with a drill, and we should be able to get a waveform. Assuming it still works, I've no idea, I just found it in the box, so we'll have to wait and see. But yeah, we'll give that a go. So if you want to mount that in the vise for us, maybe with that bit facing you, and the little plug upwards.
So there, but in the vise.
So if you clamp it on this bit here, look, because that's so if you open the vise up, that's it.
Huh?
Oh, sorry, keep going, I haven't fixed it yet, keep going. Yeah.
Oh God, that was scary.
Terrible, terrible. Right, so I'll unplug all this now. I think we've finished murdering the relay. There we go.
So you put it like down to there? Or?
Yeah, that's fine. Yeah, that's all good. Then we'll find the drill. Now, we don't need a power supply for this because it makes its own voltage. It's an induced voltage. Cool, should work. Okay, so if you want to just spin that up, see if we go, oh, look at that! All right, so we're not seeing much of a signal on there, so we need to change the timeline, the time division. Mm-hmm. So if you go onto the screen, and at the moment we're on 1 millisecond there. Look, sorry, here look, my fault. 5 milliseconds. So we need a longer time frame so we can see a few more. So yeah, just choose one of those. So with these you can't do anything wrong. You just got to play around with it. Okay, there you go. Alright, and cool. So hold it in two hands just in case it kicks back. And if you just bring your speed up slowly faster and faster. And you can see on the screen here that the taller the voltage, the taller the line, either way, that's the higher the voltage is increasing. So the faster that spins, the more voltage it induces.
That's fun.
You could play with this all day, couldn't you? I can see. Pretty cool, isn't it? And I wonder what the multimeter will give us. If we ask the multimeter to do the same thing, I wonder if it would actually give us any kind of reading. I wonder. Let's just stick that on there. Stick that on there. Oh, it's going to get really busy on there. Stick that on there. Look, that's cool. Oh, I got it. Right, that's that one. Do the same with this one. Right, Mr. Multimeter. See what he's going to give us. Right, Sam, same again.
Someone just going slowly faster.
Whatever you want, yeah. Okay, so we're on volts DC on this one. Now we can tell on here we've got a voltage going above 0 to about 3.5 volts, and we've got a voltage going below 0. So that's telling us that it's more of an AC output than it is a DC. We're not a DC waveform, we're an AC because it's alternating from positive to negative. Right, there you go. And we'll just change the voltage a bit as well. Let's just knock that down to, let's say, 5 volts. That should give us a much clearer waveform. There you go. Cool. Alright, so we'll play around with the time again. Let's just change the time to maybe 1 second divisions, because it's getting a bit bunched up, isn't it?
Yeah.
There you go.
Looks like a heartbeat.
It does, doesn't it? So the longer the line gets, the higher the induced voltage, because as that little turn wheel flicks past, it's inducing a voltage into the winding, and the faster it spins, the higher the voltage. And this is exactly the kind of waveform you'll be taking to test that component's working properly. So if you keep going, and I'll put the multimeter on AC. You can see on the multimeter there, look, on the voltmeter, we've only got, it's showing a constant voltage. You know, 1.8, 2 point, whatever it is, as you speed up and slow down. But if we were testing that distributor using a multimeter, all it's telling us is, yes, we're getting some kind of an output. Yeah. Whereas with the scope, we can see, yeah, man, you should keep going. We'll get a few more. That's it. And then I can press stop, and then we can actually zoom in, so we can actually have a look at that waveform. And you can see there, look. I mean,
it smells now.
Does it smell? Oh, is it the drill? Probably.
Yeah.
It's getting a bit old, that drill. But basically, because on the distributor we've got the 4 peaks, each one of these, let's say that was the first peak, 1, 2, 3, 4, that waveform there should be exactly the same as that one, because it's been produced by the same notch. But also, if one of those little peaks was, say, cracked or broken, you'd see a change in the waveform. So one of these would look a little bit different to all the rest. But then you'd see it repeated on every 4 because it's the same one. And you'd know that straight away that there's a problem, a mechanical problem with the actual sort of turn ring that was on there. So yeah, oscilloscopes. Bloody cool, aren't they?
It's a good tool.
Yeah. Okay, crew. Well, we had a few technical problems. Sorry about that with the old laptop. It kept freezing up on the screen. Never had that problem before, but we got what we needed to see. So that video really was to compare the use of a multimeter and the readings that it can give based on switching voltage to what an oscilloscope, yeah, you can hold that if you want, what an oscilloscope can actually provide us. And the amount of detail is just unbelievable, isn't it? You know, you can just capture a waveform and you almost like zoom in and keep going, and I feel like a train spotter because it actually,
that's so precise.
yeah, it's just, wow, it's so detailed, and it helps you to pick up on even the most minor imperfection in a signal, in a waveform. And thanks to Picoscope for sending this unit down. But this video really, it wasn't a diagnostics as such. It was just really to show you the difference between a scope and a multimeter. And also really just how bloody easy they are to use. You know, you can play around with the time base, play around with the voltage. You can't really cause the scope any harm. You've got to decide whether it's AC or DC. Plug up your leads just like you would do a multimeter, and hey presto, you've got yourself a waveform. Man, if I can do it, pretty sure most people out there can do it, you know. It's not hard. And Sam put me to shame. She was using that scope far better than I did when I first got one. I was bumbling around trying to work things out, and you know, sat at the kitchen table with a 9-volt battery, messing around. Yeah, that's what I did. But hopefully the video has been of help to you in some way. And you know, with modern cars now going down the track of more and more electronics, it's not really an option anymore whether to have a scope or not. If you're going to be doing diagnostics on cars, basically you have to have an oscilloscope, whether it's a picoscope or whatever. There's plenty of options out there. Personally, I prefer the picoscope. Yes, the channel is sponsored by Picoscope now. Thank you very much, guys. Really appreciate that. But it was my choice originally. I'm not using their scope because they've loaned me one. I'm using their scope because that's the one that I prefer out of all the scopes out there. I find it really, really easy to use. And you get free software for life. There's no, yearly subscription to pay for or anything like that. It's all free updates. And with the automotive one as well, you've got access to, God, I sound like a salesman, don't I? Sorry. But you've got access to known good waveforms, and that's critical. If you're trying to diagnose a problem on a car, and that MR2 that I was working on, I did not know what a known good IGF waveform looked like. Sure, I'd been on the net and got a rough idea, but for the MR2, I did not know what a known good was. If I'd had that, then I could have very easily compared what I was getting to the known good, and I could tell straight away that there was a problem. And you get these libraries for free. You get access to these libraries when you've got an automotive spec picoscope. And this is the 6000 series, which is pretty damn cool. Okay, Andy's been rambling enough now. We need to do a sign-off. So, it's been a whole month, and I've pretty much forgotten how to do a sign-off on my own videos. Jeez, okay, so, I think you do this bit, don't you? You do this Facebooky and Google Plus stuff and things.
All the web stuff.
Yeah, so if you stand on this side, because that works better with the thingies. Oh, there's a little cheat there, look. Okay. So, we do the subscribe bit first, don't we? Cool. Okay. So if you enjoyed the video, why not click on the subscribe button? You'll see a little gear icon turn up, and then you can tick the box and turn on notifications. Or if you're on a smart device, just ring the bell, as Eric says. You'll also find me on
Facebook, Instagram, Google Plus, and Twitter.
You will. And there's a new one. Do you know what the new one is?
The one for the shirts?
Oh, there's that one as well.
There needs
Yeah,
to be
man,
one.
there's way too much stuff going on. But yeah, if you go onto the homepage of YouTube, you'll see a little weird symbol at the end of the Facebook and stuff. And that one there you can click and you can go on and you can order an Andy Mechanic shirt. Very exclusive. And you brought me onto a new bit. There's a competition which we're going to run in conjunction with Teng Tools. Thank you, Teng. Where if you decide to buy an Andy Mechanic YouTube shirt, ladies or men's, it makes no difference, and you post a selfie and tag Andy Mechanic in on Instagram, please. You can link it to Facebook if you like. Yeah, hashtag, all that kind of stuff. Then each month you'll go into a draw to potentially win some Teng Tools, and they'll be shipped out to you anywhere in the world. Pretty damn good. So thanks, Teng, for doing that. And of course, thank you to Uniform NZ down in Invercargill for doing such a fantastic job with these shirts. I'm dead chuffed for them, actually. Very smart. Almost too smart for me, I think, really. Okay, so the last one, the last thing is we now have a Patreon account. So you can click onto Patreon. I'll put the little symbol up on there. You know how to find Patreon. It's down as Andy Mechanic. Again, there's a link on the YouTube homepage. Click on Patreon and take a look. There's some more stuff on there. If you fancy donating, then obviously click on donate and make a donation. If not, don't panic. It doesn't matter. Whatever comes our way helps. Okay, crew. Well, it's goodbye from me, and it's goodbye from Tool Girl Sam.
Next time.
Absolutely.
Next month.
No, way before then. We can't leave it another month.
Yeah,
No,
it was
promise?
too long this time.
It was way too long.
Overdue.
All right, crew. Cheers for now. Over and out.